What is happening, everyone? Coach Ishak with HawkFit Coaching and Legion Athletics, and your host for today's episode of Anabolic Radio. I'm joined today with Dr. Scott. How are you, Dr. Scott?
I'm good, man. I love the name of your podcast. I'm surprised that hasn't been taken.
Yeah, I know, right?
Has no one done that?
No one has done that yet.
It's kind of like the obvious thing, like, where are my glasses? They're on my face. It's right there in front of you. No one's picked the obvious title. That's great, man.
Thank you. I genuinely appreciate it. And thanks for coming on. If for those of you who are listening, you don't know about Dr. Scott. Dr. Scott has a PhD in applied physiology. He's an educator. He's a coach, licensed acupuncturist, and he has a license to practice Chinese medicine. And
I do.
He's also a bodybuilder, and he just recently wrapped up one of his contest preps, if I'm not mistaken.
I did. I actually competed 5 times this year. But
dang, 5 times.
Yeah. It was that's a whole other topic, different than what we're going to talk about. But I just enjoy the journey to competing, and I did a couple of national level shows, and then I just wanted to get nationally qualified so that I could do any show that I wanted, if not this past year, then the current year, 2020. So it took a few rounds of that before I could do well enough to actually get a first or second place. So I had to end up three local shows, so to speak. So it ended up being 5 total.
Wow, for sure, man. Awesome. Okay, so without further ado, why don't we go ahead and open this up? And would you briefly like to speak about the force-velocity relationship or the length-tension relationship, and how, in understanding those concepts, we can use them to our advantage when we're training?
So those are basic aspects of how muscle works that really, if you can especially the force-velocity relationship, I would say that's probably the most important and most applicable. So the notion there, and it's hard to do, I have a dry erase board over there. I believe I've done a YouTube video that we can probably link people to on the force-velocity relationship. So by its very nature, skeletal muscle in and of itself, regardless of what the nervous system is telling it to do in terms of recruiting motor units, activating fibers, or what have you, if you turn on a singular fiber, you'll see this. If you activate an entire muscle, like literally stimulate a nerve in an animal type in vivo or ex vivo type model, you can literally see the same phenomenon where there's a sort of an amount of force that can produce with an isometric contraction. There's no change in length. And more force will be produced during eccentric contraction. So the muscle is producing force, but it's lengthening while that's happening. And of course, you can force a muscle to lengthen simply by putting it in the right circumstances so that it's turned on and it lengthens because it has no choice in the matter. So if it's an animal model or like an isolated piece of muscle, you literally would have the 2 tendons connected and you would just pull them apart and measure the force as it's happening. If you're in a rehab setting or even in the gym, they've got things like isokinetic dynamometers where literally when you start flipping, what's that?
Fancy machine.
You can't. They're very pricey, actually. At least $50,000, if not more. They do a lot of cool stuff. Cybex, Kincom, various manufacturers. So let's say you're doing a knee extension. The machine can be set up so that you may start near full knee extension, and once you start pressing, it doesn't go up. It will force you down at whatever angular velocity you've set the machine up to do. So it could be 5 degrees per second, which would be brutal. So you start pushing, and the machine starts going down at 5 degrees per second. So it would be a very, very slow, basically forced negative. Or you could do that in the gym. You could have, if you had a big training partner doing knee extensions, literally you could push maximally and do a forced eccentric. So the amount of force the muscle can produce when it's lengthening and contracting is more than what it can produce when it's shortening and contracting. So there's a hyperbolic relationship there. So the force curve, I'll kind of do it. Imagine people are watching. This side is eccentrics, negative contraction velocities, lengthening contraction velocities. There's a high level of force, and then it dips down to where you would have an isometric force. And then the force drops down and sort of reaches sort of asymptote eventually where you're at max velocity. So the way I sort of explain this, and it's not people who want to be logicians might argue with the way I'm setting up this analogy, because I'm literally employing skeletal muscle as an analogy for skeletal muscle. But think about anyone who was on you have a merry-go-round when you're a kid on the playground, right?
Mm.
And you want to get that thing going. So you've got everyone would pile on, and there'd be the one kid that had to push, right, to get it going. When you first start pushing, you can tell you can produce a ton of force. You're pushing with all you possibly can. And then as it starts to go faster and faster, and that would be like faster shortening contractions on that force velocity curve, you can tell you just can't exert as much force on the merry-go-round. And at some point in time, it's going round and round as fast as you can run. And even if you stand there and try to push on it, literally you can't add any force to it. It's going by so fast. So that same sort of thing, it's a little more complicated, is going on in the contractile elements, the actin and myosin, in the sarcomeres of the myofibrils in the cells of the muscle as it's contracting and shortening. So literally the actin and myosin is going past itself so quickly that those myosin heads, when they're doing it's a chemomechanical conversion of taking ATP energy, it comes from your food, the glycogen you have stored there, and converts that into mechanical energy of force. Well, it can only do that at a certain speed. So when we talk about fiber types, for instance, if someone was thinking about that, faster fiber types have myosin that can do that at a faster rate. So they can produce more force at higher velocities of contraction. Slower fiber types, slower force. You talk about fast twitch, those will turn on and produce lots of force very, very rapidly. And whereas, so if you took a predominantly fast twitch muscle and you sent a singular impulse to it to contract, the force would go woof, would come up high very rapidly and come back down very rapidly. Whereas a slow muscle, you'd see sort of a slower increase, and then it'd come back down a little bit slower as well. So you can produce, so that's simply the nature of the force that can be produced during eccentric versus concentric contractions. The interesting thing, and this has implications for all sorts of effects of training when you're making sure you're including at least eccentric contractions, or even in the situation where they study eccentric only contractions, is that you can't really call it efficiency because you're not really doing work. It's kind of negative work when you just lower a load. If you're a physicist, you'd say that's not really work. You have to raise the load to do work. But the amount of energy that's consumed per unit of force produced during eccentric contractions is very, very, very low. So literally, you can have people lower a 1 rep max load. They sometimes in the muscle damage studies, they'll take a 1 rep max and have people do like 8 sets of 8 or 10 reps with that. And they can do that. And they suffer tremendous damage. And a lot of the fatigue actually there is not metabolic in nature. It's because those eccentric contractions are basically, and this is another poor analogy, but it helps to kind of grasp the idea, is the actin and myosin is set up to shorten. So if this is your sarcomere, you've got tons of these along the length of a fiber, and the myosin are supposed to come together as the sarcomeres shorten, the fibers shorten, the muscles shorten. That's sort of the way in which muscle is meant to go. And you can, of course, produce force during an eccentric contraction. If I had a pencil in my hand and I lowered it down, that would be an eccentric contraction. But when you're producing force and the myosin's going the opposite way, it's almost like you've got a gear system that's meant to go one direction, and you turn it on, you run up the motor, and then you force it in the other direction, and the gears get wrenched in the opposite direction they're meant to go. And that's a very raw analogy, but something that it kind of helps people understand that something is going on when so much force is produced, and the actin and myosin is doing its job to produce force, but the myosin heads are being pulled in the opposite direction than they would typically go during a concentric contraction. So a major disruption. So eccentric contractions are really economical. You can do eccentrics all day long and suffer very little fatigue metabolically, but you produce a lot more force per unit area. So in fact, if you look at isolated muscle, The maximal force during eccentric contractions in humans is probably about 40% higher than an isometric max. So you can produce like 40% more. Sometimes people just cite the frog. They've used frogs a good bit for a lot of this force velocity relationship stuff. It's maybe 70 or 80% higher in frogs. Rats, it's higher too, but it's probably 40% in humans when you can do that with E-stim in humans. So that's a tremendous amount of force. And we know that tension is one of the main drivers main pieces of the stimulus that turns on muscle growth. So if you look at overall those studies that have compared concentric with only versus eccentric only, you can get muscle growth in either situation. So you could do, for instance, in the gym, you could just lift the weight and then stop and have someone lower it for you. Typically, in the research lab, they use one of those fancy machines, the dynamometers, and it would just be a concentric only, and then you just relax back down, concentric only, or eccentric only. So you generally see in those studies that eccentric contractions produce greater muscle growth. It's not always the same. I can't remember a study that I've seen where concentric produced greater muscle growth in terms of physiological cross-sectional area or muscle volume or muscle thickness measured with with ultrasound, or fiber type, fiber cross-sectional area. It's almost either equal or it's in favor of eccentrics. And sometimes you can sort of explain that so they picked a load that was, let's say, 80% of a 1 rep max. And that was the load for concentric contractions, which is a good effort. But for eccentric contractions, that's nothing. So you really haven't relativized the loading given the nature of the contraction and what kinds of forces can be produced concentrically versus eccentrically. 80% of a 1 rep max concentrically is 80% of what you could lift concentrically versus 80% of a 1 rep max when you're doing eccentric contractions is, probably closer to 60 or 50% of what you could lower. So the intensity of loading
moving.
Yeah, so it's a matter of how do we compare? We want to set the bar equal for apples and oranges, and concentric and eccentric contractions are really very different in terms of relative force per unit cross-sectional area and metabolic demand. And metabolic stress is also an important aspect of muscle growth. Just a general overview of bioenergetics. You take in food, carbohydrates, or fat. Let's just assume we're talking about carbohydrate, and it's stored as glycogen in the muscle cell. So glycogenolysis breaks the glycogen down, and then it enters glycolysis. And in the process of glycolysis, you can produce ATP there, quote unquote, anaerobically. And then if the end product of glycolysis, pyruvate, makes its way into the mitochondria, you can produce lots of ATP, but not quite as quickly aerobically. So you produce ATP from glycolysis and oxidative phosphorylation in the mitochondria. So that's your energy currency of the cell, so to speak. That's like the dollar bills of energy is the ATP that's produced. And you derived that from the bonds in the carbohydrate that was stored as glycogen in this case. But when that ATP it binds to the myosin head, and a myosin ATPase will break that down, what that does is it creates a high affinity, sort of a charged or energized state in the myosin head. So when the myosin head has both ADP and inorganic phosphate, so the ATP has been broken down, it's no longer triphosphate, it's diphosphate with the phosphate there. It's energized. And when it binds to actin, then it will go through what's called a power stroke, and it will pull the actin in the direction that which would bring the sarcomere to a more shortened position, typically during a concentric contraction. So, but it can also bind and produce force, but go the opposite direction if you're doing a lengthened contraction. And that is, to produce force that way is not very energetically costly at all. Literally, metabolic fatigue is minimal, but the damage that happens probably simply because there's so much force being produced in that mode of contraction where it's lengthening is tremendous. And tension is important for muscle growth. The muscle soreness and damage is a whole other topic as well, how important that is. Is that important to initiate remodeling? I mean, can you literally, if you haven't had some disruption in the cell, would there even be mechanisms in place to build larger myofibrils if there's no disorganization whatsoever? Like, where do they go if there's no place to? If you want to, you have to look at the wall and look for some places to add patchwork to it to make it larger and thicker. If there's nothing disrupted, is there even something for the cellular mechanisms of muscle growth to add to and to build upon? So that's a whole other topic, but that ATP phenomenon is literally at the energy that's derived from the conversion of that ATP energy that's in that quote unquote high energy phosphate bond that's converted into mechanical force. So that's really fucking cool in my opinion. Like literally those are molecular motors as they're called. And the myosin is a big one of those. Those are used, for instance, in cells to transport things along, like microtubules. So there's cellular transport systems in all sorts of cells, and you have to move molecules along big cells, along the length of neurons, for instance. You produce molecules at one end of the neuron where the body and the nucleus is, and to get those molecules to the other end, there are molecular motors that will basically sort of chauffeur those things down. Chauffeur proteins or something else. There's a biologist that says, no, it's not chauffeur proteins, it's a different thing. But so it's very, very cool. Literally, it's the body's way of taking chemical energy and making mechanical energy out of it. It's kind of like water on a dam. Water is mechanical energy, and it gets turned to turbines and makes electrical energy. So, those. But you're right. Sorry, go ahead.
Go ahead.
Well, you mentioned an important thing that's interesting here is that you want to have both of those. It's not like, okay, well, shouldn't I just do eccentric contractions? Because the thing that we find now, and we've sort of known this to some degree for a while, is that if you look at just generally at studies that have looked at muscle growth, where they measure the growth serially down the length of a long muscle, a fusiform muscle like the biceps brachii heads, for instance, they're long muscles. You will see oftentimes, depending on what has been done, what kind of training has been done, that you'll get larger percentage growth in different areas of the muscle, sometimes in the middle of the muscle. But when they go and compare, and there's I think like 4 studies now in humans with resistance training where they've compared different modes of training, concentric versus eccentric. There's a really cool one that did kind of a hip extension exercises compared to Russian ham curls or Nordic ham curls. You know what those are, where you fix the ankle, and you let yourself. So that's a concentric eccentric type contraction in that case, and those are great. Those are phenomenal exercises. Whereas a stiff-legged deadlift basically keeps the hamstrings in a much more lengthened position. Those also will get you pretty sore. And when they compare eccentric only contraction and concentric only, you see the same sort of thing, that you'll get with concentric only greater increase in the cross-sectional area in the middle of the belly of the muscle. And so let's say the muscle is shaped. Let's say it's kind of shaped like a banana. It's a fusiform muscle, like a biceps muscle. You don't have. Let's pick another one. Let's do because usually they've done hamstrings. So these we have to use some anatomy first. So we've got sarcomeres that are in the myofibrils, which are like the strands of spaghetti in a spaghetti can, and a spaghetti can is like a muscle cell. Okay. So you could pull out one of those strands. Like, there's little sarcomeres all along the length there. And if you looked inside the sarcomere, you could see the myosin and the actin, the thin and thick filaments. So put all of the spaghetti, hardened spaghetti pieces, uncooked, back in the spaghetti can. That's your muscle cell. And now you have muscle cells that are organized into 10, 20, 100, hundreds of cells, and those are fascicles. What you can do with an ultrasound is basically look into a muscle, and you'll see that in a lot of cases that there are angles at which those fascicles connect to like a central tendon. So I know you've been lean because I've seen your website. You've dieted plenty of times.
Yeah.
Look, if you ever see someone with a really well developed rectus femoris, muscle in the middle of the quad in the front, you will see there's a central tendon to it, and the fibers come down. It looks like sometimes you see in some fish. If you can see this angle of pennation in the fish muscle. So there's a central tendon. There's an angle at which they attach, and that's a way to pack more muscle onto a central tendon. So what happens, interestingly enough, with concentrics is that angle will change and the muscle will become more rounded. So they can actually go with ultrasound and look at the angle of the way in which those fascicles of fibers connect. Mm. And the angle changes because the muscle is growing more so in the mid-belly of the muscle. Now, if you do eccentric contractions, you've got a different story. You've got lots more force being produced. And I'm going to sort of think of this sort of teleologically. What's the main concern with doing eccentric contractions?
Muscle damage.
Well, muscle damage, and there's something about those which, if we were doing sort of normal day-to-day life and you're producing high forces or resisting heavy loads that are so heavy that you can't hold them up anymore, well, that presents sort of a challenge to potentially pulling a muscle, because you're going to hyperextend a joint or overstretch a muscle. Mm-hmm. Resistance training, I always say it's an unnatural act, because you're picking something up and putting it down and picking it up and putting it down repeatedly. It's like, what do you want to do with it? Pick it up or put it down, but leave it in one place. It's really kind of a bizarre thing. We're trying to evoke a muscular callus in doing that. Mm. So if you think about the way in which muscle biology may have evolved in order to protect itself, it's if it's constantly being exposed to high loads when the muscle's lengthening a lot. The concern there would be it's going to get overstretched. Mm. And so what you can do then, what ends up happening with eccentric-only contractions, is you see relatively more growth at the ends of the muscle, which means those fascicles are getting a little bit longer. And in those fascicles being a little bit longer, you basically have a situation where you've got more sarcomeres. So let's say if you have, let's say, a muscle that's this long, and we'll just keep the math simple, and it's got 3 sarcomeres in it. So you go from this length to this length, and each of those sarcomeres has to lengthen by 33% to do that. That's not too bad, and that we're getting now to the length-tension relationship. But let's say now that you've got, instead of 3 sarcomeres, you've got 4, and you're going to undergo the same absolute length in muscle length, but now you've got 4 of those sarcomeres, and it's no longer 33%, it's 25%. I think that's right. So now each of those sarcomeres hasn't been forced to lengthen so much, and not getting to the point where you don't have good actin and myosin overlap. So adding sarcomeres basically increases the effective length at which the muscle can produce good force, and also protects it from an overstretching phenomenon when those sarcomeres are so far apart that now the myosin is no longer able to connect with the actin. So the way a sarcomere, I'm doing lots of hand waving here literally, but if these are the ends of a sarcomere, these fingers that I just brought, these are like the myosin, they'd be a little bit longer. And in the middle is actin. So there's a point where the myosin will overlap. And can you see this okay with what I'm doing? I'm hoping this works. Yeah. And then there's a point where you have, so when myosin's overlapping itself, you've got too much myosin and not enough actin for optimal force. You've got 2 myosins both wanting to interact with 1 actin, so to speak. It's not exactly that kind of a ratio. It's a 3-dimensional phenomenon. But then at some point you have, as the muscle lengthens, all the myosin that's available has actin that's available, and that's an optimal length for force production, because you have maximal possibilities for myosin and actin to interact. And then as the muscle gets longer and longer and the sarcomere lengthens, you now have in the middle here some actin that no longer has any myosin with which it can relate to produce force. So there's actin molecules here that don't have any myosin available to them, or otherwise there's myosin over here and there's no actin at that end of the sarcomere. So what you've done, if you've added more sarcomeres in series, which seems to happen with eccentric contractions, is you have more sarcomeres and you've created a longer active length at which the muscle can optimally produce force, and you've also got more force being produced at those longer lengths, which are being threatened by doing really heavy lengthening contractions. Mm-hmm. Now, from bodybuilding perspective, that's good because imagine if, just like let's say it's the biceps, imagine if all the growth was just right here and you got nothing on either side. Your biceps would just be like this giant, like an egg, like on itself, right? You want that. You want to have muscle growth as much as possible. You want to maximize the volume of the muscle growth. So concentrics tend to produce that increased pennation angle and growth in the middle of the muscle belly. And eccentrics tend to produce growth that you will manifest at the ends of the muscle belly by virtue of adding in those sarcomeres. So having both is in your favor in terms of fully developing a muscle, just in the context of having concentrics and eccentrics included in your program. So there's a study and this was done by Hather. It was my mentor Gary Dudley from my PhD, who is one of the researchers. They all did it together. This was when he was working for NASA. They're trying to figure out how to keep astronauts from losing muscle mass. That's a big deal. There's all sorts of issues. You go up there and you come back down and you've got disc use atrophy. There's no gravitation.
Oh, whoa, no way.
Oh, yeah. Oh, they lose a massive amount of muscle mass. They have some barometric pressure. They have some blood pressure issues. A lot of them will just go vasovagal when they land. They can't. They'll just pass out. That's a whole other story that maybe we can cover another podcast.
It's crazy.
Peak week strategy actually based on some of that research. So they wanted to figure out, what are the important aspects of muscular contraction in terms of what we can try to do up in space that are necessary to hold on to muscle mass. So in this particular study, they did leg presses. They measured fiber-specific growth. And they did leg presses with, I can't remember the number of sets now, but let's say it was 6 sets, the concentric only per week. So maybe twice a week for 3 sets to failure. And that's not exactly right, but it's close enough for the sake of our conversation here. So they had 6 sets and then concentric only. So they lifted and then they would let go. The subject would let go of the leg press and the experimenters would lower it for them. So there was no eccentrics at all, no lowering contractions, only the lifting. And another group did twice the volume. So 12 sets a week of lifting only with no lowering. And then the third group did 6 sets of normal lifting. Lift up, lift, lower down, lift up, lower down. They got better muscle growth, mainly in the type 2 fibers during the normal lifting. So 6 sets, concentric only, definitely inferior to 6 sets of normal up and down lifting, concentric, eccentric. When they doubled the volume, twice as many sets, concentric only, they still didn't create the same muscle growth that came with just normal lifting when you lift and lower. So the lowering part was really pretty important, especially for those type 2 fibers in this particular study. And that's sort of what you see, that there's somewhat of a type 2 preferential growth in the eccentric only training regimes that have been tested. That's a whole other topic, but that's typically what you'll see. Some of it has to do with force. Maybe it's activation. Maybe it's the violation of Henneman size principle. But
whoa, never heard of that.
Yeah, there's a couple scenarios where that can happen. One, they measure motor units in like cats. They'll put a little piece of sticky tape on a cat's paw, and they try to flip it off. And when they do that, and they measure the recruitment order from low threshold to higher threshold motor neurons, it can be reversed.
That's crazy.
So some ballistic types of things that can happen. So anyway, that's one of the things. That doesn't necessarily imply that there is a reversal of Henneman size principle per se, but there definitely shows a preferential type 2 fiber growth, which may be just of the nature of the stimulus itself being eccentric only, because remember one of the things I said, and this kind of goes to the topic, which there's starting to be a little evidence now suggesting that you can preferentially target type 1 and type 2 fibers, is that eccentric only don't produce much metabolic stress, hardly any at all. So if you're just doing eccentric only contractions, and let's say you're not violating the normal recruitment order that would go typically from type 1 to type 2 fibers.
Now, is that because the concentric range is quote unquote more metabolic?
Why there's a difference in metabolic stress for concentric versus eccentric?
Mm-hmm.
That's the unknown thing. Literally, what the bottom line answer there is, for a given amount of force produced, when I'm going to do the actin and myosin thing again. So when this myosin head binds to an actin molecule and it produces a given amount of force during a shortening contraction, that is more energetically expensive than if a given amount of force is produced during an eccentric contraction. So literally at the molecular level of converting ATP energy into mechanical energy, it's less expensive to do so when you're doing lengthening eccentric contractions versus shortening concentric contractions. So that means less muscle will be used to lower a given load than lift a given load. In fact, you can't even maximally activate a muscle during maximal eccentric contractions. Probably it just can't be done. If you look at where they've done isokinetic tests, where they have people do an isometric MVC, maximal force, and they have them to do eccentrics at varying speeds of lengthening, you only get about a 20% increase, roughly. That can be trained. There's specificity of training when it comes to type of contraction, eccentric versus concentric, and also velocity of contraction and many other things. So you can get better at it, but you probably are never able to fully activate, and that's probably a protective mechanism. If you could produce that much force, fully activate the muscle during an eccentric contraction, you probably would be risking tendon tears and really like tremendous damage, like rhabdomyolytic type of damage.
Yeah.
Yeah, at least if you've, hadn't been previously sort of preconditioned.
So would you say there are different fibers that respond better to different stimuli? Let's say, for example, like type 2 fibers are more oxidative, for example.
Yeah, there's a little bit. There's one particular study where they actually found this. I'm blank. It's a Russian. I'm blanking on the name of the first author. I have a name in my head, but it's not the right one.
It's awesome how you have a whole directory in your head.
Oh yeah, it's right there. I can see some of the figures in my mind. But yeah, basically they found that higher reps produced a little bit better growth in type 1 than type 2 fibers, and vice versa. So that kind of makes sense if you look at it. You can look at it in various ways. One, motor unit recruitment. So if you start off and load, if you start off doing, let's say, a 20 or 30 rep set to failure, and for what it's worth, if you look at whole muscle growth, typically you'll see, at least in the untrained studies with people, that taking 3 sets of 20 to 30 reps to failure gives you the same growth as 3 sets of 8 to 12 reps of failure. Several studies have demonstrated that the higher load training gives better strength gains, but overall muscle size is pretty much the same, at least in the short term. But with those lower loads, you start off the set, it's not that difficult. First 10 reps are a breeze. You're using just the type 1 fibers for the most part. So they're getting some stimulus there as they're being called upon as the set progresses. And only when you get to the end of the set, maybe the last 10 reps that are really getting hard, are you calling on some of those higher threshold motor units that are innervating the type 2 fibers. So those type 2 fibers do get activated, and they will grow. Some studies have showed equivalent growth. Just this one particular one showed a significant sort of special ability of higher load to specifically target the type 2 fibers. And there's another study that came out, but I can't remember the details of it right now. I think Brad Schoenfeld might have done it or hinted at it, but I'll have to look maybe after, and I can send you the link. So, but if you look at a higher load situation, let's say it's a 10 rep max, at least the EMG studies suggest you're activating, probably not at maximal firing rates, but you're activating almost all the motor units that you're going to activate from the get-go. because it's just so heavy. So those type 2 fibers, those are getting a stimulus from the first rep on. Maybe not, and maybe those aren't effective reps, so to speak, which is another other topic. But you're getting at least some loading on those type 2 fibers from the beginning to the end of the set, because the load is just simply so high. So that would be one reason why you get a little bit more type 2. But including the eccentric, and the important thing here for sort of practical purposes is, if you're doing a set where you're lifting and lowering, you don't want to neglect the lowering. So don't like blast up and then just like let the weight fall back down. Bounce, if you see the guys who bounce off their chest with the bench press, probably isn't the most effective way to load.
For sure.
So now we're talking about like creating the perfect rep, right? Like, how should a rep be executed? And there's actually a meta-analysis that Brad Schoenfeld actually did, and anywhere between, I think, like 2 and 8 seconds total rep speed on general. It doesn't really matter what your rep speed is, at least in studies that are out there. Now, I mean, imagine you could probably configure a rep where you do like a 4-second up, and then nothing at the extended position, and then just drop it, just like samurai or kamikaze, drop it. That's not going to do any eccentric loading. You don't want to do that. The super slow method, which some people still kind of do, it's been tested a couple of times. That doesn't seem to pan out very well for muscle growth, which is interesting because it's kind of like a blood flow restriction type of scenario. But those are I think they're just so brutally hard. Those sets last so long that people may not be able to just push themselves hard enough.
Roll up mid-set.
It's terrible. And it's the first time this is kind of a side story. The first time I saw someone doing those, it was at University of Georgia when I was in grad school, and there was like 2 open-face squat racks, and I went over to use one of them, and there's like 4 guys who were they're all doing the super slow, which was the worst fucking configuration, because each of those sets takes like 4 minutes. So they were each doing like 1 set every 20 minutes because they were all rotating in. And so I said, "Are you guys using this one?" I said, "No." So we ended up both doing bent over rows. All of these guys were bigger than me. Like literally, they all at least probably outweighed me for sure. And there's a couple of them were pretty big dudes. And I was like doing like 275 or something like that on the bent over row. And they were using like 5-pound plates on the bar, doing, this sort of like, can you tell that I'm moving? Moving? They're so slow. And I was like, it was really quite silly. So anyway, as far as rep speed, control the eccentric is pretty important. And I think you wanted to get into like the length tension curve, and that application to producing sort of the perfect rep, so to speak, from start to finish.
For sure. So how would you, or we could break off into that, or we could break off into how would you define a perfect rep?
I have a whole talk on the perfect rep. So there is no such thing, is the kind of the bottom line. Now there's a way, if you had to pick sort of the features that you would put, if you had to sort of stick to one set of features for repetition or for an exercise to have, and you would never vary from that, because I think variety is important. It's like, what's the best exercise for thighs? Well,
there's no one best
exercise, but you want to have some variety too. The one you can vary substantially, probably the best one. So the length tension relationship does play a role to some degree in some muscles during some exercises. So many muscles are set up by the very nature of the skeletal architecture, such that during a normal range of motion, so let's say a biceps curl, that you have pretty dang good actin and myosin overlap during the entire range of motion. Now, that doesn't mean that you don't see a strength curve. Like I know knee extension because I've done a lot of work with that in the past. Most people have the most knee extension maximal torque at like 60 degrees of knee flexion. So not quite a 45, a little bit further to the bottom, but that's, you put them on an isoconnect dynamometer, that's where you'll see the peak torque that they can produce. And that's not because from 90 degrees to full extension, there's a tremendous change in the overlap of actin and myosin in the quad musculature. There's some change there, but most of that has to do with the biomechanical features of the fact that you've got a quad that connects to a patella, and that patella actually serves to increase the angle at which the patellar ligament attaches to the tibia so that you can have a better angle of pull. So if your tibia is here and your patellar ligament came in a really low angle like that, that's a horrible angle for producing torque around the knee joint. Whereas if we have a patella in place, we got a better angle. We're closer to 90 degrees. So much of that simply has to do with the angle at which the architecture of the muscle as a whole and the skeleton come together to allow you to produce force. So you got a strength curve for every exercise. And ideally, you can tell this. There's some machines you get on at the gym and you're like, the guy who invented and engineered this thing never used it once, and he probably never lifted it in his life. You know, you can it's awful. It's got a tremendous sticky point. Like it's a chest press, and literally you can't get past here, and like it's so hard at the end. There's like nothing left in the range. So you go and you have this tremendous sticking point. That's because the loading curve produced by that exercise, so the load from start to finish of a normal repetition, doesn't match your particular strength curve, or probably the strength curve of many people. So the Nautilus cams, for instance, were there. It's a sort of a generic solution to try to match the torque that's produced when you have a given weight on the weight stack through the range of motion that would match then the torque that you could produce in a hamstring or a biceps curl or whatever exercise the machine is set up to have you do. But those strength curves aren't the same. It's not like always that the peak torque you can produce is 1/3 of the way through the range of motion. It's different for everybody, of course, and it's depending on your size and your own biomechanics, your own skeletal structure.
Are there any machines you find that this is like a horrible issue with?
Oh, like lines of machines. Some hammer strength are good, and some of them I don't like at all. Yeah, so there's that. And sometimes it changes. If you notice, like hammer strength machines are not the same. They have like an incline press. They probably, I don't know how many iterations they've had of that, but over the years, they make them a little bit differently, and sometimes a little more compact. Maybe they've had a compact line for gyms that weren't as big, so they had to fit more machines in. But some of them fit well, and some of them don't. So, but in an ideal situation, you would have a loading, this is in my mind, you would have a loading curve of the machine that matches the strength curve. So when you start a rep, let's say it's some sort of a chest press, and you're doing this chest press with, I think you and Dr. Israel may have talked about this yesterday, a little bit of the mind-muscle connection.
For sure.
You're doing that chest press in a way that is driven by, as much as possible, activation of the pectoralis major musculature, not the anterior deltoid, not the triceps. Literally, you're activating the pecs as much as possible and not activating the other assistant muscles. You've got a loading curve for that really nice pec-targeted type of chest press. So, and that can be done. They've done several studies now, actually with people saying, I want you to activate your pecs and not your triceps on this bench press. That can be done. They've had people do like side lateral movements and tell them don't activate your traps, giving them biofeedback or verbal encouragement. And people can learn to do that over time. And the most experienced trainees can do it better, generally speaking, than those who aren't. So you can learn how to do a chest press and make it pec targeting, as opposed, make it really a chest exercise. Although if you're a power lifter, you don't care. So power lifters might say, well, yeah, it's mainly a tricep, and it can very much be. They do that for maximal force production, using as much muscle as possible. Whereas a bodybuilder has a very different internal attentional focus to make the pecs the only muscle that's being used as much as possible. Obviously, you can't do that entirely, or you would be dislocating joints. but that's what you want. So you have a strength curve and a good machine, you can sense this, and someone who's been training for a while can sense this. You have a strength curve for a machine, a loading curve for a machine that matches the strength curve that you have when you've got a really good mind muscle connection. So you're doing that chest press, and near the end where on bench press, for instance, and some machines you have to engage more triceps just to get to full extension. In this case, that machine would have less loading at the end, so the load drops off as you get towards the end of the range of motion. And that matches the strength curve that you would have if you were just using your pecs. So the ideal situation is a cam or the levers in the machine set up such that you can match the loading curve of the machine, so that when you're relatively weak, it unloads you, and when you're relatively strong, it loads you. So let's say you have a load that is 80%, or let's say 70% of maximal effort at the beginning, and during the entire course of range of motion, that load changes, but it always stays at 70%, at least for the first rep, of what you can do at each point in time of the range of motion. The strength curve and the loading curve match perfectly. So that's a nice feature to have for a machine. Now, the other thing you can do, you can change the loading curve. Unfortunately, just the nature of gravity doesn't allow you to do this in any way you'd want to, but you can use bands and chains to also do that. So if by its very nature, let's say it's like a hack squat or a squat, whereby near the end of the range of motion, it's more dependent upon quads than glutes and posterior chain, you want to have more loading there if you're using that exercise as a quad builder. So you can literally use bands that are not elongated at the bottom of the range of motion, where you're weaker, generally speaking. That's where people, most of the time, that's a sticking point, bottom. Very infrequently, someone will be doing like a hack squat on a machine where they get like 2/3 of the way up, and all of a sudden they stick there. But that might happen if you had bands. That might be where you've added bands. If you added the bands in the right length and the right combination, you can create it such that it's as hard as it could be it's really, really hard at the bottom and in the middle and at the end, and you don't have any sticking point. So that's matching the loading curve with the strength curve. And what that does is ensures, let's take a scenario where you want to get the most time under tension, so to speak, during high efforts, and as many reps with a given load throughout the set, and you want to bring that set to failure, not because of a biomechanical disadvantage, but literally because of the fatigue invoked by the repetitions that you've done over the course of the set. So you ever have an exercise, this is the worst, where you're going and you get like 5 or 6 reps, but it's got a terrible sticking point, and you get to that 7th or 8th rep, and you just stop. That's just it. The sticking point becomes the limitation, and you prematurely end the set because you can't get. Now, if you were to go below that sticking point or above it, you could get 3 or 4 more reps, right? That's a terribly engineered machine for that given exercise, probably for you or me, or for probably most people who have a good mind-muscle connection. Now, you can maybe force past it and start using your triceps on a chest press, or start trying to accelerate through, but that's not ideal. Ideally, you see that there's no sticking point, and that you do rep after rep, and your fatigue follows a nice slow decline, as you would see in isolated muscle that doesn't have any biomechanical constraints on it. So you just get to the end, and your reps get slower and slower and slower, and like literally you have that really wonderful, ecstatic, orgasmic grinder where you literally fail, not because you run into a biomechanical sticking point, because you can't push any harder and the muscle's just so fatigued that not another rep is possible. That's a good match. And what that would mean, instead of getting like 7 reps in a premature cut short set where you stop because of the biomechanical issue, you get 10 reps. So you get 3 more of those reps, and if we want to use the effective reps idea, you got 3 more effective reps in the musculature you're trying to train. so you're not limited by some biomechanical issue. So that makes for a better training stimulus in my mind.
It's very common for people to spend their whole lives in the gym and not realize that the amount of force they exert throughout an entire range of motion differs, just because of the changes in the external moment arm length, right?
Right, yeah. I mean, a lot of people, there are people who can't even tell you what muscle they're using during a given exercise. I mean, there's that level of disconnect. But now this is not to say it's not the worst, it's not, something you never want to have a machine that might give you a little bit of a sticking point. Because as I mentioned earlier, there's also a specificity of training phenomenon here where you can actually get better at training at a given angle of across a joint. So they've done studies where people will just do like isometric training at maybe a 90-degree flexion, 45-degree flexion, and closer to full extension at a given joint. They'll get better, they'll get stronger at that angle. So some of that issue with a sticking point may be something where it's not all biomechanical. It may be that you have a neurological issue with activating properly at that angle. And so that's something you could train through, but it's also nice to have the variety. So anyone who's done, let's say you picked a certain kind of deadlift, or you have like one of your big core exercises that you do all the time, you try to progress on. And so you're going for weeks and weeks, months and months on that. You're progressing, and then you sort of plateau. It's like, okay, time to change that. And all you do is add bands or chains, or you go a little bit deeper. You just modify it to some degree. You could do maybe 2/3 or half the sets and get quite sore because it's a little bit different exercise. It's a little bit novel. And, this is a debatable topic, but in my mind, the reason why weight training, first and foremost, produces such muscle growth is because it's a novel stimulus. It's a kind of bizarre one, but it's something new and different. The nature of a stimulus that evokes adaptation is its novelty. If it's something that you've already adapted to, it's no longer novel, it's no longer new and different. It's no longer really a stimulus, so to speak, for producing at least new adaptation or greater growth. So if you come back to like changing something about the deadlift that you do, go from conventional to sumo or whatever it might be, that'll produce substantial soreness for many people who've been trained, who should have a protective effect of previous exercise, et cetera, but it's still novel and new. And so that produces a new stimulus for growth. So if you run up against the machine that has kind of a yucky sticking point, it may be so bad that it's just terrible. Like, you're just not going to deal with it. You just say, screw it, I'm not using this, I'll find a better one. But it's not the worst thing to have that in your regime. One thing I'll just say, because it popped in my head, is that I do throw out machines that have horrible friction in them, that have tons of friction on the eccentrics. That's exactly the opposite of what you want. Back to our talk about concentric and eccentric, there was a line of machine that I think Life Fitness made, and there's a couple, there are several devices that have been out there, and you can of course do this with isokinetic dynamometers. But this gym line of machine would allow you to program in the load on the eccentric versus the concentric.
And so, sort of like prime machines.
Yeah, the Prime or the Strive machines. Yeah, those allow you to change the loading curve.
Yeah, Prime machines are awesome.
Those are great. Yeah, so you can find one you like. That's awesome. Yes, it's like that. Basically took, the Nautilus cam idea and said, well, we're going to allow the cam, at this angle is going to fit some people, maybe a large proportion of them, but we can change that. You can adjust it to fit your strength curve. So those are beautiful, but it's the same on the eccentric and the concentric. In the case of these machines, they were electrically driven. There was a motor in there, and literally when you started the set, and it was somewhat limited, I think it allowed you to do like 15 reps or something like that. The first couple reps were lighter in load to kind of let you warm up into the set. But let's say you'd set the load at 100 pounds, and then you chose to go 20% above on your eccentrics. So it maybe went like 40 for the first rep, and then it might give you like 50 on the way down, and then 60, and then 65, and then 80, and finally, when you started doing 100 pounds, it would give you 120 on the way down.
Yeah, it sounds like destruction.
Yeah, but that's perfect. That matches the human strength curve in the concentric versus eccentric dimensions. Because you're stronger innately, the muscle can produce more force on the eccentric, and you don't produce great metabolic fatigue on those eccentrics. So it wasn't like doing those meant your sets became pitiful in terms of reps. They were great because you can do eccentrics out the yin yang without having much fatigue. You produce a lot of damage and you produce a lot of force. So those were phenomenal, and they're reason why I have a sense of these eccentrics being important also comes from the model that I used for my dissertation research, where we trained just one leg. This was a creatine study, and that's another topic, but we trained just one leg in these individuals. They were currently resistance training too, and we put them on a dynamometer, but we trained them with E-stim. So remember I said during the eccentrics there's natural inhibition. Your body just won't allow you to activate all the muscle that's possible. Well, when you use E-stim, it activates through the neurons, and when the muscle is turned on and you're into one of those dynamometers, it will allow a de-extension to occur at, this case, 90 degrees per second, so about 1 second up, and then it would bring you back down at 1 second per rep. 9 degrees per second. Like you had no choice. The machine was going to allow you to go up at that speed and come down at that speed. So isokinetic, iso-speed, iso-velocity, basically. So what that meant, though, is because it wasn't the person voluntarily producing those contractions, they were electrically evoked. They were artificially evoked. The muscle that was activated was on the concentric, and it stayed on the eccentric. So that intrinsic ability to produce force that's so much greater under the eccentrics was what happened during the lowering portion. So I would watch the force traces on this dynamometer, and you could see the stim would come on, and you could see the force would go up, and it would peak about 60 degrees knee flexion, and it'd get a bit lower towards the end, when they were getting towards full knee extension, and then the machine would switch directions, and it would do a force negative, and the force would just skyrocket. So I'd watch the force that was being produced during each of those reps, except some of the ones that near the fatiguing ends of the sets, was greater than maximal voluntary force. So we were producing force during probably, if we did 5 sets on a given day, we probably got in 5 sets of 10, we probably got in 25 reps at forces greater than what the muscle you could produce voluntarily.
Crazy.
But in less muscle, because we weren't activating all of the muscle with the stim. I wasn't putting enough current in there to turn on the entire muscle. So that muscle that was activated was producing the maximal amount of force that it could, which was beyond what you can produce voluntarily. Would never. That was a supraphysiological stimulus. And in the study that preceded mine, basically they compared voluntary training. One leg got trained voluntarily. The person just did all-out reps, much as they could. So there was an advantage there, too, because they're doing all-out forced negatives on every rep, voluntary. So that's a good stimulus for growth. And they compared that set for set, rep for rep with E-stim, twice the muscle growth over the course of 8 weeks.
Damn.
Now, I've talked about this before on my other podcast, but you can't really do that safely with those kinds of forces, like at home. Don't try to do it. You run into problems because the
joints.
Yeah, well, there's that. I mean, there's a funny story about a researcher. He was messing around with some things, and he put the electrodes on his delts, and he was going to try to do some side laterals. And one of the things is that the electricity comes in through what's called a motor point. So there's a density of the motor neurons, which is where the least resistance to electrical current flow is. And if the pad it's on the skin. So when you move around, the skin moves over the muscle. And it's a little bit of an issue on the quad, but not as much. The skin will slide back and forth a little, but not a big of a deal. But on the deltoid, it's sliding all over the place. So he turned the stim on. He was holding some dumbbells, and he wanted to add some stim to his side lateral. So he turned on what he thought was a good amount, and he went up like this. And now those pads got closer to the motor points, and he started activating more muscle than he was when he was down here.
Dang.
Substantially more. And he was here, and he couldn't come back down. He had to drop the dumbbells and like do a maximal like crab pose to get.
That's crazy.
Yeah. So there's safety concerns with trying to do that. You can't buy those stim units without.
I'll buy one this off season so I can blow my delts up.
Yeah, you get some people do some of those things now, and I want to look into that. But these kinds of forces we were doing in the lab were pretty high. So anyway, that shows like if you could really like kind of maximally exploit the forces that can be produced during eccentric contractions, you can get a tremendous growth stimulus out of that. So it's important to have that. So ideally, an ideal machine would be matched in terms of the loading curve on the concentric and the eccentric, and it would create greater load on the eccentric than on the concentric because you're naturally stronger when you're lowering versus lifting a load. So those machines aren't out yet. Maybe 30 years from now they'll have those.
So to reiterate some of what you said, by understanding exercise strength curves, we could understand how movements change throughout an entire range of motion, right? Some exercises are hardest in the lengthened position, some are hardest in the shortened position, some are in the middle, like a bicep curl, for example.
Right.
Would you say all muscles are strongest in the lengthened position?
Well, all muscles are strongest in closest to your resting muscle length. So at anatomical position, somewhere about there. That's pretty much where it is, but it's not entirely the case. It's probably, for most cases, if I had to sort of guess, this hasn't been studied that directly in humans, to be honest. For instance, like if you look at like the hamstring muscles. Here's a little. Have you heard of Lombard's paradox? Lombard's paradox is it's a brain teaser. So, what are the actions of the hamstring muscles at the knee and the hip?
Function of the hamstring, knee flexion.
And at the hip?
At the hip extension.
Okay, so you're sitting there in your chair, and you use your hamstrings allow you to stand up, right? So what is happening to the length of the hamstrings as you stand up?
Lengthening.
Oh yeah? Aren't you doing a hip extension? Wouldn't that shorten the hip?
When I stand up?
Yeah. Your hips are in a flex position, and then you extend as they stand up.
Right.
That shortens the hamstrings, right?
Right.
But your knees are in a bent position. They're in a flex position. The hamstrings are short. And then as you extend the knee, the hamstring lengthens.
Right.
Right?
Right.
So which is it? Are the hamstrings lengthening or are they shortening?
They're shortening.
I don't know. In the animal work I've seen when they look at biarticulate muscles like that, there's not very much of a change. That muscle is set up, and the attachment points are set up so that it can translate angular momentum across the knee joint to the hip joint and allow you to basically it sort of connects those two joints. And because you extend at the hip, which would shorten the muscle, and extend at the knee, which would lengthen the muscle's length overall doesn't change much, and it stays at a length that's optimal for actin and myosin overlap. Right. Yeah, that's the paradox. Like, how can this be, right? It's cool stuff. So, like during the squat, which can be a really good hamstring exercise, it's more of an isometric contraction than anything. I think I've seen data that maybe it lengthens during part and short, but it's not like, it's very different than, for instance, if you're just doing like a knee curl of some sort. Well, that's obvious. You're shortening during the concentric, lengthening the eccentric. So that goes back to the study I mentioned before, where they were doing the Nordic ham curls or Russian knee curls. And people, I actually stole this from Flex Lewis. There's I called it a fetal ham curl. It's a video on my YouTube people can see, which allows you to do that sort of thing. You sort of stay balled up so your body's not so far out in front of you, and you can just use body weight to do those. But that's basically allowing the body to fall forward while there's knee flexion and extension, is the Russian knee curl, the Nordic ham curl.
Mm.
versus like a stiff-legged deadlift, which keeps the muscle relatively lengthened position, but you're doing hip extension. And I don't think the change in length is as great in that case. And that has a function that's a matter of the architecture of the hip versus the knee and the excursion during the course of those ranges of motion of those exercises and how much that lengthens the muscle. So those produce differential types of growth in the biceps femoris muscle that was studied. You got more growth at the ends of the muscle, probably more sarcomere lengthening during the hip hinge movement versus the Nordic ham curl, which gave a more rounded appearance and increased the angle of pennation of those fascicles. So the answer to your question as to where, where's the best, I don't know. It depends on the exercise, depends on the muscle. Most muscles are set up to have pretty good actin and myosin overlap during most of the range of motion. During something that's normal. Obviously, if you supersede that, then you're not going to have a good range of motion or good force production because the actin and myosin overlap. But I haven't seen it studied, and it can change with training to some degree. So the main thing really when it comes down to whether it's the joint angle, that's the main thing that's determining how much force you can produce during the range of motion, or it's the actin and myosin overlap, the length tension curve. Or maybe it's just your nervous system, which isn't conditioned to produce maximal activation during the full range of motion, is you want to find machines or exercises, and cables are great for this. Talk about practical application. You can set up like cable presses, like kind of press flies with cables that are phenomenal. You see people sometimes like either you have to do a chest press with a dumbbell or you have to do a dumbbell fly. Well, what's wrong with doing a little of both? What's wrong with finding arc of motion where you feel like you're getting as much pec activation, you can have a really strong mind-muscle connection, and you're only using your triceps in as much as to keep the weight moving. They're relatively inactive. Nothing. And with cables, you can actually set those up so for instance, let's take an example with the chest. So you're at the end of the range of motion here on a chest fly or chest press. You can hold that for quite a good bit of time. That's not very difficult because the angle of force is basically in this direction. Now imagine you have cables that are coming out at an angle like that. How long can you hold if they're like perfectly at 90 degrees? So that direction, you can't hold that, right? No. So, but you're not as strong here as you might be here. So you set up, in an ideal situation, you have cables behind you, and you can set up a bench, position it forwards or backwards, so that the angle is at sort of a sweet spot, a Goldilocks zone, so to speak, for producing force during this sort of cable fly, press fly, that feels comfortable for you, that matches your strength curve when you are doing the movement that you feel you get the best mind-muscle connection with. So anyway, so that would be like the way to set things up with cables, which you can do. And literally you'll see people sometimes doing like a cable fly where they're throwing in a little bit of body English. Some of that is just, they may not even think of it this way, but I think a lot of that is an intuitive way to add a little bit of external force, so to speak, add a little bit of momentum to get through what would otherwise be a sticking point, and prolong the set and make the set a better set, as opposed to like being this robotic. I'm doing my pec flies like this. I reached a sticking point. You could pick a good exercise that doesn't have a sticking point, and those are great. But if you're trying to do a slow speed of contraction like that, and you've got a horrible sticking point, that will be what ends your set.
Do you think there's any sort of benefits in regards to proprioception or improving more motor coordination, trying to tap into those higher threshold motor units?
Yeah, absolutely. I mean, I think the mind-muscle connection can be learned. And the thing that happens, so we know that there's Henneman's size principle. There's this orderly progression from low threshold to high threshold motor units. And if, for instance, this is it's an interesting thing in the research, you will find that you can tell people use the pecs, not the triceps. And when they do lower load exercises like 40, 60, and up to about 80% of a 1 rep max, they can effectively do that. You'll see there's a relative deactivation of the triceps and more activation in the pec when you tell them to do that. But when you get to 100% 1 rep max, you don't see that anymore. Well, of course not, because it's 100% activation of everything. It's your maximal effort, maximal for tricep, maximal for pec. So the thing that is tough to do, this is really, it takes a lot of sort of mental discipline in a way that is very much a skill, is to train as hard as you possibly can and take exercises to failure, but maintain that mind-muscle connection to the largest extent possible. Because when you're getting to a failure point, you are presumably activating every motor unit that you could to move the weight that you possibly could until you can no longer move the weight and you reach momentary muscular failure. But you want momentary muscular failure in the target muscle, not in the other muscles. So you may start an exercise where you're very, very well focused on the pecs, and then you start to get towards the end, and maybe your form gets a little bit looser, and you start to involve your triceps some more, and those last reps end up sort of almost being kind of forced reps for your pecs in a certain way, or maybe even they get deactivated to some degree because you get so focused on moving the load and getting the reps and beating the logbook that you lose the mind-muscle connection. So there's a skill to doing that effectively, and the first thing that people have to do is kind of swallow the ego a little bit, I think, and use less weight.
Facts.
Yeah, because I mean, and I've done this, like I have done, and it's sort of an advanced technique that you can do intuitively. I haven't programmed it in any, like in my fortitude training regime or anything like that, but literally you can do sets that are, it's a little bit like a mechanical drop set in a way, you might say, but you take the set to failure using the purest, best mind-muscle connection you have, and then either add some body English. So let's say it's like a bent over row, and you literally go with perfect forms, slow and relatively controlled, controlling the eccentric until you're not getting anything more, and you say, okay, that's phase one of the set. Now I'm going to keep that activation in my back as much as I can and throw some body English in and basically use the body English to allow myself to do forced reps, assisting on the concentric because I'm weaker there and fatigued. But you can still extend that set doing eccentrics because you're much stronger during the eccentrics. And I think, people, now granted, obviously the long-term outcome was not the best in this case, but Ronnie Coleman was someone who people would say, look at how he, his form was awful on his back training, like all that body English and stuff he was doing. And I always had the sense in watching him, and I've watched lots of people, watched tons of bodybuilding videos, lots of trainees, trained with some pretty good bodybuilders. And you can kind of sense when someone has a really good mind-muscle connection. And I had the sense that Ronnie did. And what he was doing was creating a scenario where he was adding enough body English during those sets to have a maximal, really high level of effort on the concentric, and so that he could get the weight up. If he hadn't used that body English, the weight might not have come up, so that he could then do a controlled eccentric while he maintained the activation. So literally take a research scenario, kind of like that, what I did for my dissertation with the knee extensions. Imagine you put E-stim on the biceps, okay? And you can kind of see this in your mind's eye, or you can imagine as you did that. So you turn the biceps on, and then you basically just allowing it to contract. You allowed the person's arm to go up and come back down. You literally just allowed it to do rep after rep like that, right? That's kind of what I'm imagining that someone who uses a lot of body English could do, and it's a very difficult, and I think it's definitely a skill that can take years to figure out how to do, is you're learning how to activate the muscle, the target muscle, as with the E-stim, but in this case you're doing it voluntarily with your mind, and then you're executing the reps using enough body English to get the weight up so that you can then do a controlled eccentric. and enough body English to you really got lots of activation there. So you add those accessory muscles in, and the body English, and a little bit of the loosey-goosey form, while maintaining a good mind-muscle connection. So then in that set, in a two-phase set like that, you could silly say, okay, so I got 10 reps with 315 with clean form, and then I got some little icing on the cake. This is an intensification technique. I did 5 sloppy ones. But I kept, and then when I could no longer feel like I'm still activating my lats and my back, well, then the set's done. Then you're just being sloppy. Then you're just moving the weight around. You're doing sloppy hyperextensions with the bar at the end of your hands. That doesn't help. But that's a skill, learning how to activate those high threshold motor units with a mind-muscle connection. That's a difficult one to do.
How much do you think of those reps were created by compensation or by the actual targeted muscle?
In this case, it's the way I've sort of set up this scenario is that the actual relative extent to which the body English or the compensation, if I think I'm following what you mean by that, or using accessory muscles, leg drive, if you're doing like a row, is going to increase rep after rep. So you're only giving enough, you're trying to make each of those reps maximal, just like a really diabolical, masochistic, but he's out for your growth type training partner would do. So it's like, okay, I'm going to do 10 reps, and then I want to do 5 force reps. So, you do that 10th rep and you get here and then you go down and you can't get any more. Well, he just gives you just enough to keep it moving, and then you come back down again, and then just enough to keep it moving. And, for those 4 or 5 force reps you do, he's got to add more and more force. And then eventually by the end, and this is too far, I think, he's lifting more of the weight than you are, and that's obviously ridiculous. That's not what you want,
This is on the basis of extended failure.
It would be an intensification technique, yeah. But that's only with someone who really has developed that skill, and you don't have to do that. That's just saying that's kind of an extension of literally being able to take a set to failure, where the failure is because of the weak link being the target muscle you're trying to train. So you want that to be the weak link, because you could get more reps. And some people would do they might do a good portion of the set with good failure, and then the last 3 or 4 reps are not in that way that I was imagining Ronnie, I think, can do it, because he has a good mind-muscle connection, or someone who's really doing it. They're literally just getting more reps and not fully activating the target muscle during those reps. As you're giving max effort and your training partner is just giving you enough force to lift the thing up for you. That's an RIF on your end. The scenario that you wouldn't want to have is you're adding body English, or you're not. You can't even see this necessarily. Let's say it's a chest press. You're starting to activate your triceps more, and then it becomes basically 3 or 4 reps of a tricep movement versus a pec movement, and you're not getting really good stimulus in the pec. You're just adding reps to your set by virtue of adding activation to the triceps, and not at least maintaining a maximal effort in the pecs. You've just lost the mind-muscle connection. You're just trying to beat your logbook so you can write a higher number on the paper.
So for anyone listening, don't go in the gym and swing the weights around with a bunch of momentum.
No, not unless you have a really high sense of what I'm talking about. And people have done that. You can do that with great effect, but it's not very often that people do that. Most of the time, it's just sloppy.
For sure. So reps and sets are meaningless if you're not controlling what they're doing.
Yeah, I would say so.
Just to wrap this episode up, it's been a pleasure having you on, Dr. Scott. But would you have any, or more so, I would like to hear your thoughts in regards to regional hypertrophy and just basic anatomy and integrating your understanding of anatomy in your training.
One, we've already talked about concentric versus eccentric, and concentric contractions during resistance exercise seem to create more of a roundness and change fascicle angle in the muscle when it's growing, as opposed to eccentric actions tend to increase probably sarcomeres in series, and this manifests as greater relative muscle growth near the ends of a muscle, closer to the tendon. So that's sort of along the length of a muscle's belly, the differences that both of those types of contractions can evoke. So you want to do both. And as you said, you want to make sure you're doing eccentrics under control, so you're getting good loading and not just dropping the weight. And that you're not using momentum on your concentric. You don't want to blast into a concentric so fast that literally you've just sort of bounced the weight in the upward direction, and the rest of the rep is just following the weight as it ascends to its peak before it comes back down again. So, but when it comes to like the delts, having a posterior, middle, and anterior head, that's a function of picking exercises that target those muscles because of the angle of pull brought on by the exercise due to gravity or the cable or the machine that you're using. So obviously a chest an overhead press is going to target the anterior delt more so because from a biomechanical perspective, that's the part of the delt that has to be activated in order to do the exercise. So, with chest presses, the angle of the humerus at the shoulder joint is going to impact what portion of the pinnated muscle of the pec. So the pec is a fan-shaped muscle. Some of the fibers run in the upward direction. Some of them run in the lower directions. They're clavicular, sternal, and a costal head. So those costal fibers are more activated during a decline press. You can see EMG studies that say it doesn't matter, but there's definitely a difference if you look from a high incline press all the way down to a low decline press across. So picking the right angle, so to speak, is big as well. So angles are going to tell you what area of the muscle is being worked, especially in those that are multiple heads like that, like the delts or pinnated muscles. And concentric eccentric will change the relative regional hypertrophy in the middle of the muscle belly versus the ends, depending on if you were to do, and it's sort of a bizarre thing that you would do concentric only. That's not how most people train, but from an experimental standpoint, it's a nice way to sort of tease out the relative importance of those things, and it reinforces the idea that you want to make sure you've got good, strong contractions during the concentric, no ballistic movements, and you've got a nice controlled eccentric contraction as well. So in order to get growth along the full length of the muscle from the mid-belly down to the myotendinous junction. And good mind-muscle connection. So you're using the muscle you're trying to use. Your chest press is actually a chest press, not a triceps press.
Oh, 1,000%.
Yeah.
All right, Dr. Scott, I genuinely appreciate you coming on to the podcast. It was a joy having you on. It was a pleasure being able to ask you questions and pick at your brain. And I look forward to having you on in future podcasts. Do you have any message for the audience in regards to maybe wrapping this up or maybe upcoming projects you'd like people to stay on the lookout for?
I'm going to be, pay attention to my Instagram. I'm going to start being a little more active there. I've got sort of a journey, and I need to apologize. People probably noticed a little bit of a break. One of my dogs escaped. Someone had left the gate not fully closed, not really fully reinforced for her escape artist proclivities. So she got loose, and we had to kind of break things up. But I'll be out with my dogs doing some traveling and doing some seminars coming soon, so people can look for that and maybe find me if I happen to be passing through a town near you, so to speak.
Everyone go follow Dr. Scott. You want to see pictures of his dog?
Yeah, all three of them.
All three of them.
Yep.
For sure. Genuinely appreciate you having on, man, and
Thanks,
having you on, and I look forward to speaking with you in the near future. Thanks again.
Absolutely. You're welcome.